All right, so this particular session is related to practical implementation. Just give me a moment. Fine. So, first of all, if any questions related to the previous session, please let me know. Please write your comments on the chat box if you have any queries related to the previous session. Any queries related to the previous session? Okay, fine. So if there's no query, let's move ahead. In this session, we will be focusing on the practical implementation of convolutional neural network. I hope the screen is shared. It is visible to all. This particular session will be conducted on Google Colab. So I request all of you to please open Google Colab. You can just type Google Colab on the Google search. Open this link. So Google Colab provides you a platform, online platform to execute programs, specifically deep learning based or Python based programs, and you can create your own models. You can train those models. Some compute facility is also provided by Colab. Some facilities provided free of cost, and if you want to have higher compute facility, you can purchase from Google Colab. So let me log into my official account and then fine. So you will get this kind of a prompt at the start. What you have to do is you have to create a new notebook for writing the program for CNN. I'll give you step-by-step guide how to write, how to create a CNN, how to train it, and how to test on a data set. So first of all, I just want to you can name this notebook CNN, and we will be performing CNN on MNIST data set. I hope everybody have reached to this level. Everyone is able to open the Google Colab. If anyone facing any issue, please let me know. I request all of you to please do this hands-on session so that you can have you can learn how to code these deep neural networks. Anyone facing any issue on opening the Google Colab, opening a new notebook? I hope everybody have reached at this stage. Fine. So first of all, what we are going to do is we will be importing some important libraries. This whole code will be in Python. And so as you are aware, I'm sure you all must have learned Python. You are conversant with Python. Since teaching Python is not the scope of this particular workshop, we assume that most of you must be conversant with basic level of Python. In Python, first of all, we will import some of the libraries. Since this particular experiment we are going to conduct using TensorFlow, so I'll firstly import TensorFlow. Here, you can conduct, you can write this code on your machine as well instead of Google Colab, but there you need to install certain libraries. So just to make it easier, we are using Google Colab here. Now, next I'm going to import matplotlib. This particular library is for plotting. Those have used MATLAB, they must be aware what is matplotlib. And then inside that we'll use pyplot HPLT. And then we'll use another library called NumPy, which is extensively used for numerical calculations. So import NumPy as NP. So we have imported the important libraries. Now you can see on the left hand side there is an arrow. You can run this particular code. So there is a dashed circle that says that it is running now. Once it has completed the execution, it will stop running. Since there is no output here associated here, this is just related to importing the libraries. So you won't see any output. Only thing is you will see a green tick here on the left hand side. Now next, let's have another code segment where this code segment, we will be loading the data set. As I was telling you, we are going to develop a CNN model here. Just give me a moment. There were some comments related to the text font size. So I have increased the font size. I hope this is visible to all of you now. In Google Colab, on the right hand side here, you can see how much RAM consumption is there, how much disk consumption is there. Now, in this code segment, we are going to import the data. As I was telling you, we are going to develop a CNN model which will do digit classification, and the data set which we are using here is MNIST data set, which have 10 classes of hand written digits. So let me write. It's always good to write comments in your code so that everyone can understand your code. So it's always a best practice to write comments explaining your code. So load and three process MNIST data set. Now, how do you get this data set? So this data set is already available with this. The TensorFlow gives you the function to load the MNIST data. So basically, the function is tf teras or data sets. There are other data sets as well for which it gives you access to download the data set. So data sets, then name of the data set. You can see there are multiple options you are getting here, like California Housing, CPART, and Fashion MNIST, IMDb, and MNIST. So we are using MNIST here. And then there's a function called load data. So once you type some letters, you will get suggestions of that particular. So this is the function. Now, how do we want to take this data? So I'll use xtrain and ytrain. I'll tell you what exactly they are: xtrain and ytrain. And similarly, we'll get xtest test. So this is the output format in which this particular load data function will give us the output. If you want to see the syntax of this load data, this is the syntax of this load data. You can see here on the uh, on the bottom, you can see the returns, and it gives you returns as xtrain and ytrain and xtest and ytest. So what exactly is xtrain and ytrain? As we're aware, in the previous session, we talked about the input as well as the corresponding label. So we split our data into training data set and the testing data set. Training data set is for training the model. However, once the model is trained, the test data is being used to evaluate the performance of the trained model. So that's the syntax of this function, load data. And also there is a description of this data set is also given. This data set is of 60,000 images, and the dimension of each image is 28 cross 28. As you are aware, we discussed about this one when we were discussing image classification using neural network, where we had 28 cross 28 dimension grayscale images, and there are 10 classes for each. Now, next, once we have loaded this data, we want to normalize this data, because the pixel intensities will be in the range of 0 to 255. But it's always better to have normalize for best performance by these models. So we will normalize this training data as well as the testing data. How do we normalize? So let's train comma test. Let's normalize it. Train divided by 255.0, since it's a float type of data. Let's test divided by 255.0. So what exactly this step is doing, let's write comment on this one. So it is normalize the values of pixels. So this is about normalizing. We have loaded the data. So data, then normalize it. Now, this particular MNIST data, the images are of two-dimensional since they are grayscale. Now, we want to feed them to a CNN. So we are adding an extra dimension. We are making them RGB by adding a blank third dimension to it. And so how do we add that? Xtrain is equal to Xtrain. Since it's a grayscale one, we want to have our third channel in this one. So we can just add the third channel here by defining new axis. New axis. Similarly, the same thing we can do for test data. X test is equal to X test, and we have added a new dimension to the test and the train data. Fine. So, and then let's first execute it. It will load the data, normalize this data, and add a new comment or access. Let us run it. You can see here it is downloading the data. Okay, so there is a question here. What is the use of adding the new dimension? So because since we are making a CNN here, so CNN will expect the three-dimensional data. So that's why we are adding a new axis here. The original MNIST data is the images in the original MNIST data is of 28 cross 28. It's not a three-dimensional image. I mean, it's not a RGB channels. So that's why to feed it to the CNN, we have added a third dimension to it. Now you can see here, this data has been downloaded from this particular path. Now, once this is downloaded, let us see what is the dimension of this data which we have prepared. So, with the help of shape function, we can see what is the dimension. So, firstly, let's see what is the dimension of the train data. So this is the dimension of the train data. 60,000 training images of dimension 28 cross 28 cross 1. This third dimension we have added here to make it three dimension. If you want to see the dimension of this data, which we have directly downloaded, so let me do one thing. Let me comment it. And see the dimension of the original data. So we'll run this particular section again, and then we'll see what is the shape of this. Now you can see here the original MNIST data is of this dimension. We don't have third dimension of this particular image. Right. So that's how we can see we have added the third dimension to it. I'm just uncommenting it and running it again. And now seeing the dimension of this. Similarly, we can see the dimension of test dot shape. It will also be the of same dimension, but the number of images will be different. See, so this is the test training data. This is test data. As you can see here, in the description of this MNIST, you can see 60,000 training and 10,000 test images are there. So what we have done so far, we have imported the important libraries. We have downloaded the MNIST data. While loading this data, this function itself gives us the bifurcated data in training and testing sets. Then we have normalized it. After normalizing, since all of these images are of two dimension, but to feed them to the CNN, we need to have these images in three dimension. We should have three channels. So we have added a new axis to both of them. And finally, we have seen the shape of these two training and the test data set. Now, next step is to build the CNN model or to create the CNN. Let's create the CNN model. CNN is convolutional neural network, as which we have discussed in the previous session. So as I told you, CNN is combination of different type of layers, like the convolution layers, pooling layers, and the flatten and the dense connection layers. So what we are going to do here is we will create this model. So what is the syntax? How do we define the model? So model is equal to, we will use this TensorFlow, which is a platform for creating these models, training and testing these models. So we are using TensorFlow dot eras. And what kind of model it is? It is sequential model. Let me tell you what exactly sequential mean. Sequential mean there will be a sequence of layers, one after another. Firstly, convolution layer, then pooling layer, then dense layers, and so on. So that's why we are defining the sequential model. And in the sequential model, whenever you see, whenever you want to have more detail about any of the function, you can just highlight it and see the description of that particular function. So the Google Colab is providing you total description of each of the functions which are being imported here. So we are creating a CNN model which is sequence of layers, and the first layer always keep track of these brackets. Sometimes there you might have a problem with open and close brackets, and there will be error by the model. So firstly, we are going to define the convolutional layer. So tf dot eras dot layers. So what all layers we have here? Layers dot. Now you will see different type of layers like activation layer, average pooling, 1D, 2D, 3D. We want a convolutional 2D layer, and then we will define some parameters to this convolution layer. So what could be the parameters for this convolution layer? The number of filters, the size of the filter, and stride, padding. All these arguments we need to define. If we don't define all of these arguments, the default value of these arguments will be taken by this function. So as of now, firstly, we will define the number of filters. So we are taking 32 filters in the first layer, and the dimension of each filter is 3 cross 3. And what kind of activation we are going to use with this activation? We will use the ReLU activation, and then we will define the input shape, input underscore shape, and you are already aware the shape of the input is 28 cross 28 cross 1. And then so that is how we have added the first convolution layer, which has 32 filters of 3 cross 3 dimension, and activation we are using ReLU, and we are defining the input shape as 28 cross 28 cross 1. Next, we are going to add the max pooling layer, tf dot layers dot max. I'm sorry, tf dot keras dot mistake in the spelling. Tf dot keras dot layers. Let us see what options it shows us. Layers dot. So there are a lot of options. So we can use max. You can see we are getting options of max pooling 2D, max pooling 2D, and we need to define the filter size. So we are using 2 cross 2 here. And here also we need to have a comma. In this, here we have created the max pooling layer, and since it's a sequential one, next layer we are going to add here. The next layer will be again the convolution layer, pf.keras layers. Now on 2D convolution layer, and again we need to define how many filters we are going to use. This time we are going to use 64 filters, each of dimension 3 cross 3. And what kind of activation we are going to use here? Activation is equal to L. And then 4. Now you must ask me why we are using 32 filters here, 64 filters here, why the dimension 3 cross 3, or why the dimension here is 2 cross 2. So these are basically the hyperparameters which we define while we are defining the CNN model. So these are basically these parameters defines what type of model we are using here. So it's open. I mean, you can use any number of filters. You can use any dimension of the filters. It is up to you to decide which type of filter, how many filters are performing well for your problem or your classification task. Fine. So next, again, we are going to use a max pooling layer. Max pooling. Max pooling 2D. And here also the dimension of the filter layer, though we call it filter, but it's not a filter, but the dimension in which we will be performing the max pooling is 2 cross 2. So what we have done so far, we are defining a CNN model. Firstly, we have used the convolution layer, which has 32 filters of 3 cross 3. Then we are using a max pooling layer with a filter size of 2 cross 2. Then we are using a convolution layer which has 64 filters, each of 3 cross 3. Again, we are using a max pooling layer. After this max pooling layer, we are going to flatten this output. At this stage, we have a cuboid kind of output. However, now we want to flatten it or vectorize it in a single column. So we'll use a flatten layer. Let's start flatten. F is capital here. Flatten. And there is no parameter to be passed to flatten layer. So we can just flatten the cuboid feature map at the output of this max pooling layer. Why we are flattening? Because we will feed it. I mean, we need the output as 10 nodes, and those 10 nodes will contain the score for a particular class, and whichever node will have highest score, the input will be classified to that particular class. So once we have flattened it, now this after flattening it, we will use the dense or fully connected layer of dimension 64. Dense layer, and this dense layer is of dimension 64. What kind of activation we are going to use here? value, and we can also name this particular layer. So suppose I want to name it as features. Why we have named it as features? Because these layers, the earlier layers, convolution, max pooling, convolution, max pooling, flatten, they have extracted the features. And now here at output of this layer, we have features extracted by these layers. Now, finally, we will go to the output layer, and what will be the dimension of the output layer? Of course, there are 10 classes, so the dimension of the output layer, yes, it will be a dense layer, but the dimension will be equal to the number of classes, which is 10. Now, one important aspect here is what kind of activation function we are going to use. We will use the softmax type of activation. And why softmax here? Because softmax helps, softmax is, you can say it's kind of classifier. You can use it as a classification. It will classify the given input to a particular class if the score of a particular output node is highest. So now with these steps, we have created the CNN model, which contains two convolution layers, two max pooling layers, two dense layers, and one flatten layer. Now, this is just the creation of the model. Now, let's see whether it gives me some error or not. So, it is, yes, it is giving me error that I cannot use name as capital N. I think it should be small n. Yeah. Let me see if it compiles or not. Yes, it has compiled now. There is just a warning here. There is an error as such. I hope everybody has reached to this level. If not, I'm just taking a 2-minute break, and I request all of you to please type this much code and run it. If you face any issues, please let me know. So I got a query. Can you summarize it again? Yeah, fine. So quickly, I'll just summarize what we have done as of now. We have imported uh, some of the important libraries since we are using TensorFlow to build this model. So we have imported TensorFlow as TF. We have used matplotlib, which will be used for plotting the outputs. And the next library we have used is NumPy, which will be used for numerical calculations. Now, the first step is downloading the dataset, the MNIST dataset. And for that, we have this function load data. So TensorFlow gives us this facility, this function to load the MNIST data. And the syntax of this function load data, the return values are xtrain, ytrain, and xtest and the source. It already bifurcates the data set into train and test. Xtrain is the input, ytrain is the corresponding label. Now, once we have executed this, this gives us the whole data set. Now we need to normalize the pixel values. Since the range of these pixel values is 0 to 255, so we have to normalize it by 255. As I was telling you, the dimension of these images in this MNIST data set is 2-dimensional. They are grayscale images. So to use a CNN, we need to make them 3-dimensional images. So we have added a new axis to train and test data. Now you can see that we have a third dimension as well, apart from the dimension of the images 28 cross 28. Here we have 60,000 training images and 10,000 test images. Now next what we have done is we have created a CNN model, and for creating CNN model we need to define a sequence of layers. So we use tf.keras.sequential, and then one by one we define the layers. The first layer is convolutional layer, which contains 32 filters of dimension 3 cross 3, and we are using ReLU type activation function. We are defining the input shape to this particular layer, which is 3-dimensional, 28 cross 28 cross 1. Then we are using max pooling layer. Again, we are using convolution layer. This time we are using 64 filters. After that, we are using max pooling layer. We are flattening the feature map, and then we are using 2 dense layer. The final dense layer has only 10 nodes because there are only 10 classes of physics, and here we are using softmax to classify the input to this dense layer. So now we have created this CNN model. Now next we are going to compile this model. Compile the CNN model. So for compiling, since we have already defined this model here, this is model. Now we can use this object of this model dot compile, and model.compile uh, we will define the optimizer. So as I was telling you, optimizer basically trains the model, which implements the gradient descent and the back propagation algorithm. So one of the popular optimizer is Adam. There are other optimizers as well, which we can use here, and we need to define what kind of loss function we are going to use here. So here we are using cross entropy loss. You can use another type of loss function as well, based on what kind of model you are training. And while evaluating the training performance, we will use a metric. And what metrics we will be using? We'll be using accuracy as a metric here. Fine. So that is how we are going to compile this CNN model, which we have created in the code block. Let's run it. So there is no error. That means we have successfully compiled it. Next, we are going to see what model we have created. So let's see the summary of the model. So model dot model dot summary. So it will tell us what model we have created here. So let us run it. This will give you the complete summary of this model. This model is sequential model. It will tell us what all layers are there, what is the output shape of each of the layer, and how many parameters are there in each of the layer. So the first layer was convolutional layer, found 2D. The input it takes is 28 cross 28 cross 1. which we have defined here. Now, in the previous lecture, we have seen the formula for calculating the output feature map dimension. So by applying that feature map calculation dimension formula, we can find out the output dimension of this convolution layer. Then we have max pooling layer, it's 2 cross 2. So that will be the output dimension. Why the parameters are 0? Because there are no learnable parameters in max pooling layer. The third layer is again convolution layer, where we are using 64 filters. So it will give us as output of 11 cross 11 cross 64. Again, we are using max pooling layer, then flatten layer, then the features layer. You remember we gave the name as features, that's why it is showing us the name features. It is 64 here. And you can see the number of parameters in this dense layer, they are very high. However, the parameters in convolution layers are comparatively very small because we are using the weight sharing mechanism here. So there are total parameters 1,21,940. These many parameters are there in this particular model. Now the next step is to train this model. So let us train this model and just commenting what exactly we are doing in each of these 4 blocks. Training the model. So how do we train this model? So we will use the fit function model.fit, and what all we are providing as input to this fit function. Of course, the training data x_train, the corresponding labels. Then we will define the epoch, how many epoch we are going to run this training. So epoch is nothing but the whole the number of times the whole training data set is provided to the model for training. Let's say we will be providing the training data set for 5 times during the training process. That's why the epoch is 5. Then we do the validation during the training itself. So the same data set which we are using here for training will be split into training and validation, and we are giving the ratio of this validation split. So 10% of the data will be used for validation during the training process. So model.fit function basically trains the model. We are giving these arguments to this function, the training input data, corresponding label, number of epochs. We can vary the number of epochs based on the loss or accuracy we will get during the training. And this is how much data we are going to use in validation. So let us train this. Let us see how it is going to perform. Let's run this particular code block. I think there is some problem here. Let me see. Epoch. Epoch is giving me some error. Let me see. So it's not epoch, it's epochs. We need to have S here. Let me run it again. Now you can see it has started training. It is telling you this is epoch 1. And now you can see during the training, the accuracy is going up and the loss is going down. So in epoch 1, let's see how much accuracy we are going to get and what will be the loss value. So the whole objective of training is to minimize the loss with respect to the parameters. So this training process is adjusting those filters, adjusting the parameters, these many parameters, 1,21,930, and in such a way that this loss function is minimized. This loss value is minimized. This is epoch 1. At the end of this epoch, we have received 90% training accuracy and loss is 0.32. However, the validation accuracy is very high and loss is very low. Now, the second epoch is running. So in the second epoch, we have received very high accuracy and you see the loss is minimized. It's very low. We'll see some more epochs. So how do you decide how many epochs you are going to use? This depends on how quickly the loss is being minimized and how the accuracy is increasing. Now you can see we are getting above 99% accuracy and the loss is also very low. So hopefully by completing 5 epochs, we will be able to achieve almost close to 100% accuracy and loss will be minimized close to zero. So the whole data set is divided into batches of the images, and one batch goes together for training, and then the accuracy and loss is calculated. So this value signifies the number of batches. Now, the last epoch, you can see the accuracy is very high. That is in this particular epoch. You can say that the model is almost trained. Loss is almost minimized. It is close to zero now. Fine. So the model is trained, and finally we have received very loss value and very high accuracy values. Now, next step is once we have trained this model, we need to want to evaluate it on the test data. Let's have a new code block. Now I need to evaluate it, and I will see what is the test loss and what is the test accuracy. Test accuracy. We use the function model evaluate. What are we going to pass here? The test input and the corresponding labels. So, and then let us print it. Since we have calculated this, let us print the accuracy value. Post accuracy. We have calculated test accuracy as test accuracy. Let us evaluate it, how much accuracy we get. How to set hyperparameters, if any method is available to set hyperparameters in this. I mean, there are various methodologies to set these hyperparameters. So, some grid search. There are n number of methodologies to find out the best hyperparameters. But yes, the best way to find out these hyperparameters, the optimum values of these hyperparameters, is to try and test. So let us see how our model perform here. We are evaluating the performance on those 10,000 test images, and the test accuracy we have got is 98.83% on the test set of MNIST datasets. Fine. So now what we are going to do here is we will plot some images, and we'll see what are the predictions and what was the actual label of these images. So firstly, what we are going to do is we will do the predictions. So predictions, predictions means the model output for the corresponding test images. So that we will store in this variable predictions is equal to model dot predict and x underscore test. So this is the set of test images, 10,000 images, and this is the label model output. That means the label will be the class number from 1 to 10. So for each of the image, all of those 10,000, we will calculate the prediction or the model output, and then we will see what is the ground truth which we have provided. The ground truth is y test, and the model output is prediction. So that is how we calculate the prediction. So we have calculated the value of predictions for each of the image in the test data set. Next, let's define a function. I'm just giving you a glimpse how we can use a function in Python. So let's define a function for plotting the image, and we will use this function afterwards for plotting the images from the data set. So let us define this function. This function will basically take ith index. So if this index tells you which image it is, then this is a new variable which is nothing but the predictions. This we will pass on to this function, the predictions array. The true labels, the y test, true underscore labels, and of course the image which we will be passing. So this is the function which we are defining here. Now, so true underscore label comma ing is equal to, so this particular true label is an array. This image is also an array of the image. So we are extracting individual labels and the image from ith index. So true underscore label, and the index is I, and also image from the ith index, which we are again reshaping it to 2 dimension. Reshape it to 28 cross 28. Try to remember we converted the shape of this image to 3 dimension, but now just for simplicity of plotting it, we are converting again to 2 dimension, that is gray scale. Now we will plot and define certain features whether we want to have the grid. So we'll make it false. Then yes, we will have X sticks. Similarly, we will have Y-X. And then finally, we will use IMShow, the plt dot IMShow, plt dot IMShow. And what all arguments we are going to pass here, the image, and what kind of map we want to use. We want to use the binary because this is just a grayscale image. So just the black and white or grayscale. And also on this image, we want to show the predicted labels. So predicted underscore labels is equal to np dot arg max. I'll tell you what exactly it is. Predictions for underscore arg. What we are doing here is for this particular image, we are from this prediction array, we are finding the maximum value, the one which have maximum value, that label will be assigned to it. So whenever we are calculating this prediction for particular image, if you can see the dimension of this predictions, it is 10,000 cross 10. So 10,000 is number of images, and for each of the image you have 10 values corresponding to each of the class, and one of the class will have the highest value, and that will be the class of this particular image. So what we are doing here is we are finding the maximum value out of these 10, and that will be the label of this particular image. Now we'll define what color we are using here. Color will be blue if we have correctly identified if predicted underscore label is equal to the true label, true underscore label, else it will be red. So what we are doing is we are creating a function for plotting the image. Along with the image, we are also plotting the predicted label as well as the true label, and we are defining the colors of these labels. If the label is correctly predicted, we will plot it in blue, otherwise we will plot it in red. Fine. And let's have the labels for the axes as well. So plt dot x label, and we will use, these are some of the syntax we will get to know slowly. Uh, predicted underscore label, and on this front. I think this is not, uh, this is required to show the predicted label and will be equal predicted label, and then we are defining 100 into np dot max predictions. I'll tell you, just type the code and then I'll tell you what exactly this means. As I was telling you, this prediction array contains 10 values corresponding to each of the image. Now I'm trying to find out the maximum one, and the class to which this image belongs will have the maximum value out of those 10, and I'm multiplying it to 100 to make it percentage. And array dot one f. So since it's a float value, this will be percentage. So I'm calculating the score as a percentage for each of the class, for the class to which it belongs to, or it is classified by the model. And then I'll define it as true. Um, there is some syntax error here. Interminated. I'll, I guess now it is correct. Let me run it. Plot image expected this. So when we define the function, we should use this column. Now we have correctly defined this plot image. Now what we are going to do is we will display the initial 15 test images along with their predicted label as well as the true label. And then for doing so, we will be using this function. So what I'm doing here is, let us plot, let us plot first 10, let's plot, let's say 15, let's plot first 15 test images with the predictions. Fine. What we are going to do here is we will define a figure, plot fi figure, and what will be the figure size. Fig size, this you can choose whatever you want to choose here. Suppose I'm choosing this figure size 10 plus. Right? Okay. Now I'll run a for loop for 15 images. Run this for loop for 15 images. And what I'll do here, I'll call this plot image function, which we have just defined. So how I'm going to do that? I'll plt dot subplot. Those who have used MATLAB earlier, they can appreciate it. Subplot what will be the dimension? 3 cross 5, since there are 15 images, and I'm using this index I plus 1 since it starts from 0, the plot, and now I'll call that function plot image, which we have built written above this particular code block, in which I will pass the index of the image. I'll pass the predictions of ith image. Remember, this prediction is of dimension 10, score corresponding to each of the class for a particular image, the true label, y test, and of course the image, which is x test. And then this we have done. Now I will do some beautification. Plot type underscore layout. It's not necessary we do this, and then show this plot dot show. Fine. So yes, this might be little confusing, but let me explain it again. Fine. We have defined a function plot image, and what does this plot image do? It takes the test image, it takes the true label of that image, it takes the prediction of the model, and remember the prediction of the model have 10 values corresponding to each of the class and ith index of the image. This image is not individual one. This is the whole training data, testing data set. Now we are extracting true label and the image for ith index from this particular array of labels and the image, and we have already reshaped it to 2 dimensions for displaying the grayscale version. Then how do we find out the predicted label? So out of those 10, I'm just finding the highest value, because the model will classify that image to that particular class to which it has highest score. So that I'm extracting here. And then I'm also displaying the predicted label and the true label in different colors. If predicted label is equal to true label, it will be displayed in blue. Otherwise, it will be displayed in red. And I'm also displaying the percentage value of the prediction. And finally, by using this function, I'm displaying the first 15 images. So let me run this plot image function, and then let us display those 15. There is some issue here. What is the issue? Let me see. Plot image predictions I. Cannot access local variable true label where it is not associated with a value. Let me see where is true labels. Just yeah. There was some syntax errors here. Is using it as true labels here. However, it is true label. Similarly, for predicted labels, I was using it as predicted. Now, what we have done, we have plotted those 15 test these things. You can see here, this is the image. In plot X label, you can see the predicted label, the score in percentage, and I have to I need to display the I miss it. I think we didn't display the true label also here. I somehow missed that. It's not a problem. So this is a 7, and the image belongs to 7 as well, and it is 100% scored to this particular class. 2, 1, 0, 4, 9. This is 5. This is 9, 4, 1, and this is 0, 6, 9, 0, 1. So all are correctly predicted here. So I think that's how we have used a CNN model to classify the digits, the images of MNIST dataset. So if you have any queries, please let me know. I'm here to address those queries. I'm sure everybody is able to execute this code. Still, if you are not, we'll share these notebooks to you, and you can use these notebooks and do your experiments yourself. So now, any queries related to this practical session? Let me see the comments. Um, any other query? Error in last cell. Let me show you the last cell again. Yeah. So please carefully revisit your code and match it with what I have written here. If you upload any handwritten image, can this model be able to predict? Yes, definitely. Only thing is we need to have the dimensions same as 28 cross 28, and we can do the predictions. Someone has shared his collab. I'm not sure whether we'll be able to access. Let's try. I'm opening a Google Colab of Jasveer Singh. Let me see what error he has done. Two labels is not defined. Yeah, so it's the same problem which I did earlier. What two label is two labels. So here you have used two labels instead of two labels. So that's the problem. I think now you can execute your collab. I hope the speed it is clear. Fine. So any other queries, please? If there are no other queries, I think we can conclude here. Thank you. Thanks a lot. Bharti, sir, I'm getting the same error. Same error cannot access local variable to label where it is not associated with the value. So I think there is a typo spelling mistake in the variable true label. Somewhere it is true labels and somewhere it is true label. So I think you need to rectify that. Everywhere you should have use the same variable name. So could you please share the code? Yes, definitely we'll share the code with all of you. Fine. So I'm just signing off. Thank you. Still, if you have any queries, you can make a note, and tomorrow we will be meeting in the second session. We can have further discussions related to this. Thank you. Thanks a lot.